So the topic for this video is going to be working with exponents and roots. When you work with a value that's an exponent, it's going to be a small number to the right of a base number. Sometimes, besides being called an exponent, these are called powers. The base is the large number, the value that the exponent has as its power. For this one, we have 2 as the base and 3 as the power. Often these will be called cubed if it's to a power of 3. If you have something that's to a power of 2, it's usually called squared. After that, the powers don't have specific names. If we're looking at 2 to the third power, or 2 cubed, that means I'm going to multiply the base number with itself 3 times. This exponent only tells you how many times you see the base number multiplied with it. You're not going to see that exponent anywhere in the problem, so I don't notice the number 3 itself. I just notice that there are 3 2's being multiplied together. With the GRE, you do not have a power key or an exponent key on the calculator that's online. So you have to go back to the definition of what a power is and what it means in order to calculate it. So anytime you see something taken to a power, you're going to have to go through and multiply that number with itself that many times to get your value. Some other things that you're going to notice for exponents is if you have something to the 0 power, it's always going to equal 1. Let's take a look at the pattern to see why. So we started with 2 to the third power. 2 times itself 3 times. So that gave us a value of 8. Next we have 2 squared, which is 2 times 2, or 4. 2 to the first power is usually just written as 2. You don't put the 1 as the exponent. It's understood to be there. But if we look at what's happening with these different patterns each time, notice that to go from one to the next, we were dividing it by that base 2. Here, to go from 4 to 2, again, I divided by 2. So if I'm looking at the pattern, I'm going to expect that to go to the next one, I would divide by 2 again. And 2 divided by 2 should give me the value 1. That's what we said, anything to the 0 power is equal to. And so you can notice that from the pattern that you see. I'm going to use that same idea with looking at the pattern to show you what happens if you have a negative exponent. A negative exponent does not give you a negative number. A negative exponent tells you to put that base in the denominator. So I'm going to write it as 1 over 2, and then it's going to change from being a negative exponent to a positive exponent. I can do the same thing with the next one. 2 to the negative 2 power means I have 1 over 2 to the second power. So by putting that in the denominator, you no longer have negative exponent. 1 over 2 squared is going to be 1/4. And if we want to check to see if this is going to work with our pattern, if I take 1 and divide it by 2, I am going to get 1/2. And if I take 1/2 and I divide it in half again, I do get 1/4. So the pattern does look like it is working. So you don't have to necessarily memorize them if you realize you can find them using the pattern. Let's look at a few other examples. The tricky thing about working with these is that the base number can be positive, can be negative, and the same is true for the exponents. It does make a difference if there's parentheses around your value or not. So for the first example we want to compare negative 3 squared to negative 3 in parentheses being squared. Does it make a difference? Anytime you are working with an exponent, the exponent only goes on the value in front of it. That negative is outside the number. It's like having negative 1 times 3 squared, or negative 1 times 9. So I'd get a negative 9 for this value. For this one, the square is outside the parentheses. So it's telling me to take everything I have in the parentheses and multiply it with itself. Here I've got negative 3 times negative 3, and the value would give me a positive 9. So depending on how it's written does make a difference in whether you would get a negative value or a positive value in this example. If the exponent is an odd number, things might be a little different. I can do the same idea with negative 3 cubed and compare it with that quantity negative 3 cubed. I also want to show you what happens if you have negative 3 with a negative exponent. So here again, we're working with negative 3 to the third power. The 3 is only on the 3. The negative is outside of it. So you can think of it as negative 1 times 3 cubed. 3 cubed will give me 3 times 3 times 3. So for this example, I end up with negative 27. If I want to compare it to the quantity negative 3 being cubed, I have negative 3 times itself 3 times. Negative 3 times negative 3 will give me positive 9, and 9 times negative 3 will give me negative 27. It's different if you have that odd exponent. That does make an important difference, because here a negative number is still negative when you're taking it to that odd power. But it was different when we were working with the even power. Let's take a look at the last one, which is negative 3 to a negative exponent. Now again, the negative is out front, so it's like negative 1, and I'm multiplying it with 3 to the negative third power. We mentioned that the negative exponent doesn't necessarily make the number negative. It just puts that in the denominator. So I could rewrite this as 1 over 3 to the third power. That's where the negative exponent comes in. 1 over 3 to the third power will be 1 over 27, and I still have to multiply it by the negative 1. So negative 1 over 27. This one does end up being negative, but the reason it's negative is because of the negative out front, not the negative that's with the exponent. So here's an example of a GRE question that would use these powers. One of the types of questions we have is quantitative comparison. They're going to give you two columns, quantity A and quantity B, and they're going to have you go ahead and determine if the two quantities are going to be larger, the same, or you can't determine it. Quantity A is greater, quantity B is greater, the two answers are equal, or the relationship cannot be determined. So I want to evaluate what I have first. And here's where remembering what happens with that negative out front is important. I have a negative with a 2 cubed, and it's being divided by 2. Now remember, if you have that negative with a 2 to the third power, it's like having negative 1 times 2 to the third power, or 2 times 2 times 2. On top, I'm going to get negative 8. And when I divide negative 8 by 2, I get a negative value, negative 4. I want to compare that to the other quantity, which is negative 2 being squared. So I'm taking the entire group, because that exponent is on the parentheses, and multiplying it with itself. Negative 2 times negative 2 gives me a positive value. So for this one, I'm comparing negative 4 and positive 4. Positive 4 is definitely going to be bigger. So for my answer, I'm going to choose quantity B. The other thing we want to take a look at are working with roots. Just like you have adding and subtracting that are opposite operations, or multiplying and dividing that are opposite operations, anytime you work with powers and roots, they're also going to be opposite operations. So you can think about them as undoing each other. Squares and square roots, cubes and cube roots, etc. are going to be the opposites. So for an example, we have 5 squared, 5 times 5, which gives you 25. So the opposite of taking something and squaring it would be using a square root. So the square root of 25 is going to undo that squaring process, and it gives you back the value of 5. Often, the square root will be written like this, but you could technically have that little 2 there to show you it is a square root. Most of the time with a square root, that's not included, just like the power of 1 isn't written. Anytime you have a different kind of root, for example, a cube root, or any higher value, you will see that little number written on the side of the root. So let's come up with some values that are going to be perfect squares. Since we're looking for things that once they're squared, they undo each other, I want to know what those are, because I'll look for those as factors when I'm doing my work. So 1 squared is just 1. 2 squared is 4. 3 squared, 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. And 10 squared is 100. Since these are all going to be perfect squares, anytime I'm looking to break something down, I may look for factors of 1, 4, 9, 16, 25, 36, 49, 64, 81, or 100 as a factor, because that way I know if I'm trying to take a square root, it comes from a perfect square. Once you take a square root, one of the things that's possible is that the original number that you squared could have come from either a positive value or a negative value. For example, let's look at the square root of 4. I could think of the square root of 4 as being the square root of 2 squared. So the square root and the square cancel, and I get the value 2. Or I could think of the square root of 4 coming from the value negative 2 squared, because negative 2 times negative 2 also gives me 4. So when I take the square root and the square, I could end up with negative 2. It is possible, anytime you're working with a square root, that that number underneath might have had originally a positive number squared, or it could have had a negative number squared. Most of the time you're going to be working with this one, the positive number. It's called the principal square root. One of the things you have to watch out for is that you cannot take square roots of negative numbers in the real number system. And for the GRE, the only system it's going to be working with is the real number system. So if you see something like this, this is not going to be possible in real numbers. The reason is because there's no number I can multiply with itself to end up with a negative. You can multiply a negative with itself and get a positive value, or a positive with itself and get a positive value. But there's no way to multiply a number with itself and end up with a negative. Now notice this negative is under the square root sign. It is possible to get one, but it's not in the real number system. Perhaps you are familiar with the value I for an imaginary number. And it's defined as the square root of negative 1. The GRE is not going to be working with any imaginary numbers, so you're not going to need to worry about it. But what about a negative out front of your square root? What if you had negative the square root of 4? Is that different than the square root of negative 4? Yes. Again, like we were talking about with those powers, if you have that negative out front, you can think of it like negative 1 times the square root of 4. If we're only working with the principal square root, that's the positive one, I'd have negative 1 times 2, and it would give me negative 2 for my value. If you were looking at all possible ideas,